want to start? Okay. Yeah, it didn't start at 1, so the people saying ones, it did start at 15.
Let's do 20.
20, sure. Oh, thanks. So 20, tan squared of x equals 1/3. So first thing I'm going to do, square root both sides. So that's going to give me plus or minus, and then 1 over the square root of 3. So I'll split those into two equations, one for the positive, and then one for the negative. So I'm going to do tan inverse of 1 over the square root of 3, and then tan inverse of negative 1 over the square root of 3. Everybody okay so far there? Okay. So now I'm going to go to my unit circle and find the places where tangent is equal to 1 over the square root of 3 and where it's equal to negative 1 over the square root of 3. So if I do that, I'm looking for a place where, remember, tangent is y over x. So I'm looking for some place where I have a square root of 3 in the x part, because I need that to be in the denominator. So I see that at pi over 6, for example, tangent would be 1/2 over square root 3 over 2. And if I multiply by the reciprocals, I get 1 over square root 3. Everybody agree with that? So that's going to tell me then that x is going to be pi over 6, as well as 7 pi over 6. And then for this part, I'm going to have 5 pi over 6, and also 11 pi over 6. So that's my part A. For part B, you might be tempted to just slap on a plus 2 pi k to each one of these 4. And that's not incorrect, but we can do a little bit simpler of a job with that. Notice how far is it from pi over 6 to 7 pi over 6? Pi, right? 6 pi over 6, right? Or just 1 pi. And if I go then from 7 pi over 6 back to 1 pi, if I go on my unit circle from 7 pi over 6 back to 1 pi, how far is that? Also pi units, right? So basically I'm running into a solution every pi. So rather than doing that as 2 pi k to each of them, I could just do it as pi k and just have one answer here. Similar over here. Ann, are you okay with that? I don't think I probably would have marked down had you done 4 separate ones with 2 pi k's there. Okay. So we have pi over 6 is here, right? And 7 pi over 6 is here, right? Yep. because remember the fundamental periods for tangent is pi rather than 2 pi. So I can, it's not wrong what you had written if you did 2 pi k's after each of them, Ann. It just, we can write it a little bit simpler. So it's like not reducing a fraction or something. It's not like you've given the wrong answer. It's just, it's not the simplest answer you could have given. Okay with that? All right, for C, obviously all my answers for part A are still answers for part C. Everybody agree with that? And then I also have to be concerned about things that I can, from 0 to negative 2 pi, or negative 2 pi to 0, I can also have answers in there. So all I'll do is subtract 2 pi from each of these. And that's another set of answers. I just got that by subtracting 2 pi from the previous 4 answers. So D, obviously these first 4 answers are still going to be answers in part D, because 0 to 2 pi is part of the interval for D. Now, not all of these next 4 answers are going to be answers in part D, because D is only from negative pi to 0, right? Not negative 2 pi to 0. So this guy is too small, and so is that guy. Those are both less than negative pi. So I'm not going to include those, but I will the other 2. And then I have one more part of the interval for D to worry about. And that is for the parts that are from 2 pi to 4 pi. So I can find those just by adding 2 pi to each of those first 4. Yep.
Wait, so you're at 17 points, or is that
13, 19, 17, 23. Where did I get those numbers? I added 2 pi to each of these first 4. So basically the way I thought about this was, those are my answers from 0 to 2 pi. These are my answers from negative pi to 0. And these are my answers from 2 pi to 4 pi. When I union that all together, that is just negative pi to 4 pi. So that's the way I thought about it. The reason I thought about it that way is because I could use my answers from part A, I could use my answers from part B, part C, and then all I had to do was figure out those answers. That's why I thought about it that way, is because it involved me having to do less. Does that make sense? And you happy with that? Was it mostly the pi thing that was bothering you? Right, the pi part. Yeah, okay. Raul. We do not know that yet. We are going to learn that, not in this chapter, but soon. Yes, go ahead, Joanne. Jacqueline. 26? Sure. You're going to laugh at it, though, I promise. Okay. And what's sine over cosine? And when I go to my unit circle, that's pi over 4 and 5 pi over 4. So part B is just pi over 4 plus pi k. Remember that I can do that because this is a tangent one. I don't have to do two separate ones. I can just do one of these infinite solutions. For C, I'm still going to have my answers from part A, but then I can also have stuff from negative 2 pi to 0. So I can subtract 2 pi from each of these. So that's going to give me negative 7 pi over 4 and then negative 3 pi over 4. And then for part D, I'm going to have my answers from part A. I'm going to have my answers from part B that are greater than negative pi. Well, there's only one of those. It's just the negative 3 pi over 4. And then I need my stuff that's between 2 pi and 4 pi. So I can just add 2 pi to the first two answers. And there's that. What's up?
Where do you get those numbers from?
The unit circle? So tangent is like x over y on the unit circle. So I'm just looking for a place where the x and y coordinates on the unit circle are equal.
Okay, so you find those on the unit circle, and then to get B, you find the difference between pi over 4 and pi over 4.
No, not really. So for part B, I want to find everything coterminal to those two answers. But tangent's a little bit easier, can be a little bit simpler, because the fundamental period for tangent is pi and not 2 pi. So the values repeat every pi units. So I just need one of them and add pi instead of 2 pi.
Okay, I get that. And then for C,
This is my answers from part A, because this is the stuff from 0 to 2 pi. And then this is, I subtracted 2 pi from each of those two answers, and that's going to give me my stuff from negative 2 pi to 0.
so you subtract 2 pi?
Yeah.
Okay. And then for the next one, I don't have to do that one.
So this is my answer for part A. Bella, the next part, that's our answer from part C, but I had to throw out anything that was less than negative pi,
And because it wasn't in the range.
because it's not in the range that was requested. The range is from negative pi to 4 pi. And then this part here is the stuff from 2 pi to 4 pi. So what I did is I took my answers from part A, and this time I added 2 pi. That's it. So once you have your answers for part A, everything else is like based on those answers. So the other part should be quick once you've got part A. Jackie, you good with that? This is a rather common trick. Having not ever seen it before, I would not be totally expecting anybody to really have come up with that on their own, having not seen that trick before. But it's one that we'll use in solving rather frequently. So just kind of tuck that one back in the back of your head there somewhere that that's a useful trick to be able to use. Okay? What's next? You can just ask.
So, where in life are we going to use these numbers? Like, what
Great. Sure. So, say that you are like an automotive engineer. And you have like, you're building like part of your drive shaft for your car. And say that like you figure out there's like some flaw in your drive shaft. And you want to know like, and maybe there's multiples. And you want to know like at what points when this thing is spinning is that flaw going to like run into something. This is a... Stop talking. If you want me to answer these kinds of questions, which I'm happy to do, I don't want to hear like a bunch of riffraff being yelled over on top of my explanation. Okay? If you have legitimate questions about it, raise your hand and ask your legitimate question. Ask it to me. Don't shout crap to your friends to be funny or silly or whatever else. But at this point, hopefully you kind of see where I'm getting at, right? In terms of like an everyday adult that's a non-engineer, no. But most of the stuff you do in school is not stuff you do as an everyday normal adult, right? Like, I'm going to write a persuasive piece about Julius Caesar. Like no one needs to do that, right? So again, can we stop? I have a point here I'm coming towards. Okay? In general, most of the specific skills you learn in high school are not real world applicable. Overwhelmingly, right? There's some that are more so than others, but a lot of them seem very like esoteric, right? Here's why. So that's the question. Why are we doing this? Because what it's trying to do is like teach you how to learn. And mathematics is one of those things because it's so logic based and so systematic and so general. It's developing cognitive skills that are really, really important. So, like, let's say you have a process and you want to decide what order do I need to do things to make this the most efficient process. Those are the same kind of skills and cognitive skills you're developing in your mathematics course. And, like, that's, at the end of the day, like, that's where we're trying to get to with a lot of this. But, yeah, if you're not going to be, I mean, even, stop talking, please. Stop talking, please. Even if you are an automotive engineer, you're not solving this equation by hand. You have a piece of software that you're using to do all this stuff anyways. Now you have to understand like how the software works and how to use the software, but you're not going to be using the like specific skills over and over and over again. But you have to know enough to like if you make a mistake to look at your answer and go, that ain't right. Which is part of the, like why we do this as well, because at 17, most of us don't really know what we're going to do. Even after you graduate from college, a lot of people end up in jobs that they didn't intend. So, like, that's the other half of it, is trying not to, like, eliminate possibilities of what you can do in life at a really early age. Is that an acceptable answer? I tried not to give you a BS answer. Okay. Well, it's a circle. Yeah, you can scale it so that it is a unit circle, but yes. All right. Are there other problems from here that you guys want to talk about? Jacqueline. 27. So cosine of x is equal to 1. x is equal to cosine inverse of 1. Yep, so for part A, there's just one place on the unit circle where cosine has the value of 1. That's at 0. So for B, it's just going to be, it's just 2 pi k, because 0 plus 2 pi k is just 2 pi k, right? C is going from, notice that here the intervals matter quite a bit. Notice both of these are brackets. So here, my solutions are 0 minus 2 pi, 0, and 0 plus 2 pi. That's kind of mean. D, notice that here the interval is parenthesis on the 4 pi. So here my answers are just 0 and 2 pi. This 4 pi doesn't work because it's not in the interval. So this was one that was really kind of, you really had to pay attention to whether they were brackets or parentheses. Does that feel okay there, Jackie? You're welcome. Who's next? No, it's okay. That's what this time is for. I'd love to. Do you have a preference? I can do both. So sine of x is equal to 0. So x is the sine inverse of 0. So I'm going to go to my unit circle and look for places where the y coordinate is 0. That happens at 0 and pi. So that's my answer for A. For B, notice this is one of those rare occasions where the distance between our answers on the unit circle is pi. Like 0 to pi is pi, and then pi back to 0 is another pi. So I can condense this down into 0 plus pi k, or just pi k. It's not wrong to write 0 plus 2 pi k and pi plus 2 pi k, but it's more than you need. For C, remember that we're going from negative 2 pi bracket to 2 pi bracket. So I have answers, if I subtract 2 pi from 0, I have 0, I have pi, and then if I subtract 2 pi from pi, I have negative pi. And then because 2 pi is in a bracket here, unlike this one where the 2 pi was in a parenthesis, I also get 2 pi on that one. Is that okay, Jackie? You don't like it. Tell me what's going on. So, observe in part A, the 2 pi is a parenthesis, meaning 2 pi is not an acceptable answer in our range. In part C, the 2 pi has a bracket at the end of it. So 2 pi is an acceptable answer for part C. And on the unit circle, this point here is 0, and it's also 2 pi. Okay with that? Okay. And then for part C, again, the interval here is negative pi to 4 pi. So our answers are negative pi, 0 pi, 2 pi, 3 pi. Oh, sorry. That one. My apologies. At least I wrote them in alphabetical order, right? Jackie, what's up? For B is all real numbers. Well, pi plus 2 pi is going to give me things like pi, 3 pi, 5 pi, 7 pi, 9 pi, etc., right? If I'm just doing pi k, I'm going to get 1 pi, 3 pi, 5 pi, 7 pi, 9 pi, etc. I'm also going to get 2 pi, 4 pi, 6 pi, 8 pi, etc. So I'm getting 0 plus 2 pi, n pi plus 2 pi, which is one thing instead of two separate ones. Like I said before, it's not wrong to list them separately. It's not standard, if that makes any sense. It's like writing like 4 over 2 instead of just 2. You know, like it's not 4 over 2 isn't wrong. It's just not the simplest. Yeah, it's just not the simplest way we could do it. Are we okay with 18? You said which other one? 22? Oops. So tangent of x equals 0. So we just want the tan inverse of 0. Remember, tangent is equal to y over x. So this is going to be the same thing as where y is 0. So the answer to sine or tangent inverse to be 0 is the same as sine inverse of 0. So I can literally just use my answers from 18. And if you did that on like a test or a quiz or whatever, I'd give you full points for that still. If you're like, oh, this is really the same, like you'd need this line explaining to me why it's the same question. But if you can show that it's the same question, you don't need to do any more work for me. If it's something you've already done. And I think that happens a couple of times in the homework where maybe at first glance it doesn't look like a problem you already did, and then you do a little rearrangement, it's like, oh, this is a problem I already did. You can always just cite, like, this is the same as problem 7 or whatever, and just be done with it. Is that okay, Jackie? Okay. And you're okay with me just skipping out on actually doing the solving since it's the same thing? You're good with why it's the same thing? Okay. What's next, guys? Did you say sleep? You guys are funny today. All right. So we do need to talk a little bit more about solving. Yeah, I'm not kidding. So okay. I need you guys to stop talking, please, and please pay attention, because it's a little bit subtle and can be a little bit tricky. And there's a little bit of detail in here that if you don't catch can become a problem. So what we're worried about today are situations where I have stuff going on inside of my trig function. Okay? So I'd start this problem the same way. I would take the sine inverse of both sides. And I'm going to go to my unit circle and locate the places where sine is equal to, or sine inverse gives me 1/2. Everybody's okay with that? Okay. So that's going to give me two equations now. So when I multiply both sides by 1/2, I'm going to get that. Everybody okay there? Okay. So here it doesn't seem like that big of a deal, right? Where it becomes a bigger deal is when we, say, are doing the same problem, but this time we're looking for x's on bigger intervals. And in fact, here we're not even done yet. We're going to come back to this in a moment. And I'll show you why we're not quite done with part of this part. So if we do the same thing, eventually we're going to get that 2x is equal to pi over 6 and 5 pi over 6, right? So I can write 2x is equal to pi over 6 plus 2 pi k, and then 2x is equal to 5 pi over 6 plus 2 pi k. Everybody okay there? Because we're solving it for all real numbers. And now when we multiply both sides by 1/2, that 1/2 distributes to the angle as well as the 2 pi k. We see that. So, everybody kind of see that? You're going to say yes? All right. So why does that, coming back to this answer, why do I have more answers here? Well, if I do pi over 12 plus pi, I also get 13 pi over 12. And that's still between 0 and 2 pi, isn't it? And if I add pi to this one, I get 17 pi over 12. And that's still inside of 0 to 2 pi, isn't it? If I add another 2 pi, clearly I'm going to be too big. But these problems, where I have a coefficient on my x, are problems where I would do the part B of the homework first, and then use that answer to get your parts like C and D. Okay? So let's say that we, again, are doing the same problem, but this time we're going from, I don't know, was this the, I think that's the range I get for part B. And let's say that we've done like the part B. Let's look at how we would go about getting our answers for this. Okay? So, my first answer is going to be if k is negative 1. If I'm subtracting pi from this. Similarly, if k is negative 1 here and I'm subtracting pi. Then I'm going to have when k is 0, and then I'm going to have when k is 1, and then I'll have when k is 2, and then I'll have when k is 3, but if I go to k is 5, I'm going to be too big. Wait a minute. Yeah, sorry. Thank you. K equals 3. If I go to k equals 4, it's going to be too big, right? Because now I'm adding 4 pi, which is definitely too big. Sam.
How can you add 3 pi to sine and get the coterminal angle?
Because here, the 2 on the x is causing a horizontal dilation. So the period is shrinking from 2 pi to 1 pi. So now you have coterminal things every pi units instead of 2 pi units. Yeah, you'll get twice as many answers. True. But that's why you're getting more answers. Should we do another? Sure. Yeah, we'll certainly, we have one comment. Yeah. Something, yeah. Yeah, I understand, for sure. So you guys should work on the next block of these solving ones. Hopefully you feel a little bit better.